Feel it at the end.
That's a pretty good idea.
Right. It should be. There's always a little bit of a delay on my end, so
Yeah.
but it
It
should be.
says it's up on the Zoom, and I'm just waiting for it to
Yep,
populate
there
on
we
YouTube.
are. Okay, I'm going to close
Hello
this.
world.
But we are live.
Huzzah!
Voila! So welcome to a special edition of Space Weather Unplugged. We have a wonderful guest here, Carina, who works with the Moon to Mars mission at the Space Weather Analysis Office. There's a lot of words here.
Yes, it's the
Physics
longest acronym.
Science Division at NASA's Goddard Space Flight Center. It needs an acronym for the acronym.
It does. It's like the longest thing ever.
But we're super happy to have her here because obviously we love our space weather forecasters because us Aurora chasers rely on them for many things. So she's here to talk to us about what she does. But before we do that, I want to give a big shout out to Tanya. It's her birthday. So happy birthday, Tanya.
Happy birthday, Tanya.
Happy birthday!
So I will hand it over, and then if we have any questions, we'll keep a look on the chit chat, and we're looking forward to hearing about what you do.
Awesome. I'm gonna make sure that it allows me to share my screen.
Yes, I think I gave you the privileges.
Sweet.
Yep, there we go.
Alrighty.
Yay!
You have to let me know if you can see everything.
I can see.
I won't be able to see you guys, just as a heads up.
That's all. It's all good.
Awesome. Alrighty. So, thank you for having me. This is very exciting. And as mentioned, I'm Carina. I work with the Moon to Mars Space Weather Analysis Office at NASA's Goddard Space Flight Center. And I'm going to talk to you a little bit about the team and what we do at the M2M group. So here's a little overview of what we'll go over, but we're going to talk about what is the Moon to Mars Space Weather Analysis Office, what we do, what tools we use, and what we populate. And then I'm going to walk through an example event and then just give a shout out to some of our collaborations. So this is a lot of text. I'm sorry for that. I'm going to try and make sure that there's not a whole lot of text on the rest of this, but our mission statement. So the Moon to Mars Space Weather Analysis Office conducts real-time space weather assessments to support the validation and development of new capabilities for understanding space weather impacts on NASA robotic missions and human exploration activities, which is a mouthful. But essentially, we were created to support NASA's human and robotics missions. We support NASA's Space Radiation Analysis Group, which is located at NASA Johnson Space Center down in Houston, Texas. And we work very closely with the Community Coordinated Modeling Center, which is mainly at NASA Goddard, and then NOAA's Space Weather Prediction Center, SWPC, which I saw you guys got to have a nice chat with Sean Dahl previously. So shout out to them. They are fantastic. And then M2M is kind of in this weird situation where we act as the proving grounds for capabilities that will eventually transition to operational agencies. So a lot of what we do is not meant to be official forecasts or anything. It's a lot of more so this test bed sort of environment. And then human in the loop activities that were previously known to be part of the Community Coordinated Modeling Center, aka CCMC, their experimental space weather forecasting team were transitioned to Moon to Mars. And so I know that one of the common misconceptions with our team is that we are part of the CCMC. We're more like a sister to the CCMC. So our two groups are funded separately and work separately, but we collaborate together. So a lot of the tools that the Community Coordinated Modeling Center provide, we populate. However, we are not attached to the CCMC. But we love them. They are fantastic. So a little bit about us. We're located within the Space Weather Laboratory that is within the Heliophysics Science Division at NASA's Goddard Space Flight Center here in Greenbelt, Maryland. We were created in June of 2020 to help fill the need to predict space weather hazards for NASA's crewed missions outside of Earth's magnetosphere. So specifically, we have been helping with the Artemis mission. So we did a 25.5-day support with Artemis 1, where we worked 24/7 supporting the Space Radiation Analysis Group with predictions related to solar energetic particles and validating that models are working well in real time. And then on a day-to-day, M2M analysts work 7 days a week to provide near real-time space weather analysis support for NASA human and robotics missions. It doesn't matter how small or large, or which direction the CME is going. If it is measurable, we will analyze it. So that includes any CMEs that are less than 200 kilometers per second. If we can get a measurable front, we will analyze it. You may not see it published anywhere, but we have the analysis on our end noted in an internal daily log. And then M2M plays a vital role in space weather advancements towards support for missions beyond Earth, and our collaborations allow M2M to assist with the advancement of modeling efforts for SEP events. So this is more so a breakdown of what the day-to-day looks like as part of the Moon to Mars Space Weather Analysis Office. So we like to say it's an observe, analyze, model, and document sort of framework. So when it comes to observing, what are we talking about? Well, we look at solar imagery in real time or near real time. We analyze these images usually up to 15 hours a day. So during the weekdays, we work 7 a.m. to 10 p.m. We have coverage with an analyst on shift at any point during that time. And then on the weekends, it's 8 a.m. to 10 p.m. So we have one less hour during the weekends, but otherwise we're working 7 days a week. It doesn't matter if it's a holiday. If there's a mission, we'll go into a different sort of coverage. So with the James Webb Space Telescope launch, we supported that, which was a Christmas Day launch. So we were actively working on Christmas Day, supporting the launch of James Webb. And then same with Artemis. Artemis went right through Thanksgiving. And so we supported that as well. And that was 24/7 operations. So for observational data, though, we use the Integrated Space Weather Analysis System, aka ISWA, which is provided by the Community Coordinated Modeling Center, or CCMC. It is a visual display of observational data and model outputs hosted by the CCMC. And basically, I could probably show it after I go through all the slides, but it's this great tool, and they just recently updated it. So it's got a lot of new cool uses, but it's kind of like a one-stop shop where you can create your own display of all of the images you want to look at. You can look at Solar Dynamics Observatory, you can look at SOHO imagery, you can look at stereo imagery, GOES imagery. There's even MAVEN data on there now, so you can look at just about anything and everything on there. Discover data, ACE data, so kind of just a mix of things, whether it's imagery or timeline data. And so we use all of that when we're doing observations. Now, if we were analyzing, so if there was an event, we will analyze it. So whether it is a flare that goes off, a solar energetic particle event, a coronal mass ejection, if we're seeing an interplanetary shock, so any arrival signatures, a magnetopause crossing, that's usually modeled. So if the models say, hey, there's a chance that the magnetopause of Earth is going to cross into geosynchronous orbit, which could impact satellites, we have notifications we send out for that to NASA missions. Geomagnetic storms, we will note those and add those into databases as well and notify on those. Radiation belt enhancements, and then coronal hole high-speed streams. So there's kind of a multitude of things we look at. And then when it comes to modeling, our models are then used to forecast impacts on the space environment. So I'm sure this is probably what most people have seen that the Moon to Mars group provides, are those NLIL models. So our CME parameters that we analyze and we measure, like you saw on the previous slide, what we see up here on the left, you can see us measuring a CME here. We literally lasso the CME to try and get parameters and then can get a measurement on it. And then we can use those parameters and enter them into the model simulation you see on the upper left here. And so we'll add those CME parameters into a WSA Enlil plus cone model, which propagates the CME through the solar system and predicts the time of the arrival at Earth and the intensity of a geomagnetic storm for us, as well as arrival times at other locations where NASA missions may be located. And so we have all of that modeling. And then this bottom one kind of is just a quick highlight of one of the SEP modeling frameworks we have, which is the SEP Scoreboard, which are hosted by the Community Coordinating Modeling Center. They have a group of ones that are open to the public to use. And then we have ones that are on our end that we use specifically to support the space radiation analysis group. And then when it comes to documenting, so once we've modeled it, we will add this into the DONKI database. So DONKI is the space weather database of notifications, knowledge, and information. It's a catalog of space weather phenomena observed in near real time. And so we will add that information into there. And basically, DONKI is an incredible database that is used by the community, whether it is the public. I would say it's more mainly geared towards anyone using it for research or for modeling purposes. This is a really useful catalog for them to do that. And since M2M started, it's become much more populated. So we are actively entering in data to it anytime during our shift. So you will usually see anything published in there between 7 a.m. to 10 p.m. 7 days a week. And then on the weekends, it's probably more closer to 8 a.m. to 10 p.m. But if there's a major event, sometimes we can't help ourselves and we stay on later and then we end up working through it. And so you may see us posting stuff later after that 10 p.m. Eastern time. But for the most part, it's either 7 or 8 a.m. to 10 p.m. Eastern that you will see updates there from us. There are some automated notifications that come through there. And so you may see like a flare entry that just says M5 that will pop up, and that's automatically created just to notify whether or not we're available to enter that immediately for NASA missions. So there is some automation with it. But for the most part, it's manually updated and manually entered into the DONKI database. And then M2M, as I mentioned, issues notifications for significant events predicted to affect NASA's satellites, which includes, but is not limited to, missions near Earth, Stereo Ahead, MAVEN, the Parker Solar Probe mission, OSIRIS, APEX, which was REX at one point, but is now APEX, Solar Orbiter, the Lucy mission, the Psyche mission, and all the way out at Juno, which is hanging on to Jupiter. So with that, I'm going to walk through an example event. So this was back on June 8th of 2024. We had an active region numbered 13697, which was located here in the southwest, around South 17, West 68. And it produced back-to-back M-class flares. So we had an M3.3 and an M9.7 flare. This event did end up causing solar energetic particle events detected by the GOES satellite, the SOHO satellite, and the Stereo Ahead satellite. The resulting CME was large, it was very bright, and it was a very fast CME. And then once we measured it, it did give us predicted arrivals to Earth, Lucy, Parker Solar Probe, Stereo Ahead, Mars, which is where MAVEN is, and OSIRIS APEX. And so we can look at this event a little bit here. So if you look here, you've got this really nice flare, the double flare there. You can see a lot of the movement there. And then I should have had it loop, but I don't think it does. So you can see that really nicely there. It's a really pretty eruption, a lot of filament material out of that. And then we can see the EUV wave a little bit here. So there's this really nice wave of material being pushed as that eruption erupts. So we can see that again here. So lots of material. And this was a very impressive looking CME. So, but what it did cause, and I remember I worked this event, a really quick solar energetic particle event. So we had, this was prior to the flares, and then right after the flares, everything jumped up. So what you're looking at here is the GOES primary proton flux data. And basically we've got time on the bottom here, and then the values of how high this event was. And so the greater than 10 MeV channel here crossed its threshold, and then it kept going down, and then which I believe is in the cyan. Sorry, it's here, the cyan color. Usually it's red, but in this one it's cyan. So this crossed threshold, it spiked up really fast and went very high above threshold. So its threshold for NASA missions follows the same threshold that SWPC produces, which is the 10 PFU threshold. So this line right here, it crossed that pretty quickly, only a matter of minutes. So we can see, I believe the flares were around 250 or something. And so we had a pretty quick, I think it took 10 to 30 minutes for us to cross threshold for some of these. And then the 100 MeV channel is the red one, which crossed pretty quickly as well. So its threshold is 1 PFU here. And so it very quickly crossed that as well. So we had a very energetic event with this solar flare, or these two solar flares. And then similarly at SOHO, so this one is looking at the SOHO data, we had this huge increase, and the thresholds are actually dashed lines here. So you can see the 10 to the -1 threshold here. And basically both of these crossed that threshold pretty quickly. And then at stereo ahead here, which we would look at the red line here, which is the 13 to 100 MeV, this also crossed its threshold, which was 10 to the -1, which would be right around here. Relatively quickly. So it was a very energetic event. And to see that, we can see the resulting CME was very large, powerful, and you can actually see the particles overwhelm the satellite imagery here. So what we're looking at is the blue is the C3 chronograph on SOHO. The red is the C2 chronograph on SOHO, so it's a little bit closer in. And then superimposed on that is an SDO image in the 131 angstroms, which is typically what we use to look at solar flares. And so you can actually see really closely the flare go off, and then the resulting CME come out and push all the particles and accelerate those. So it was quite the event. And then the CME fits, we can see we lassoed the CME, and this was kind of just giving us what the bulk may look like. And so the fits provided speeds anywhere from 1,100 kilometers per second to 1,500 kilometers per second, depending on which feature we tracked. So you may see in the DONKI database, sometimes we will have bulk analysis and shock analysis. And so this would be considered a bulk analysis. So it's holding onto the bulk of the material versus a shock analysis. If I can read it. Oh, uh-oh. Oh, no. Let's see.
Oh, no.
Right. We crashed.
It happens.
Right. Got too excited.
Right. It's all that solar energetic particles.
Let's see if we can get this going. There we go. So with the shock here, am I still sharing? Can you still see my screen?
Yeah, you're good. Okay,
perfect. So the shock analysis here, we can see is much wider. It's grabbing more of that faint material. It's usually the ones that tend to be more Earth directed. And so I tend to see people grab on Twitter. They really love to hold on to the shock analysis. I'm like, no, that's not accurate of the bulk of the material. It should be the bulk analysis. So if you see me shouting about that on Twitter, I'm so sorry. We just want to make sure that you're grabbing what is probably more accurate to the main material that's being pushed by the CME versus the shock. Which is usually the reason we do analysis of bulk versus shock is for actually SEP modeling purposes. So when we do a bulk analysis, that's usually what we're going to notify NASA missions on. We'll say these are where the arrivals are expected and everything. That's going to be based off of the bulk analysis, which is what this one is. Versus when we do a shock analysis, this is going to help us produce some of the SEP model outputs, which then get populated onto the SEP scoreboards that are hosted by the CMC. So once that was analyzed, we were able to get this beautiful model. And so what you're looking at here on the left is a top down at the ecliptic plane. We've got Earth and a yellow dot, which I find personally confusing. I don't know why Earth is not either green or blue, but it is yellow in all of our models. So Earth is here, the sun is in the middle. We've got the CME is the blob passing through here, and we can see that there was an impact at Earth modeled. There was an impact at Stereohead, which is this red square here. Parker Solar Probe is on its way back towards the sun in this passage here. We can see that Lucy had a possible impact, and then we have Mars up here, and then Osiris Apex back here. And so this was the bulk analysis, but the shock more likely covered even more than this. So with that, and then further kind of going back to the analysis sides of things, we ended up seeing the arrivals in the near Earth environment and then at Stereohead. And so we can see that we had this increase and we saw this change from the background magnetic field data to an increase where we probably had this arrival come in. And then you can see this, I didn't know it would do that. We have this density increase here. We have a solar wind speed increase, and then we have a temperature increase. So we can actually see that this arrival occurred right around this time here. And this is the near Earth environment data. So this is ACE data. And then over here, this is the Stereohead plot, which is impact/plastic data. So the impact data is all in this top section here, which is very clearly red. And then there's actually Discover/ACE equivalents just behind it. So you can see the timing difference of when arrivals occurred. And so we can see here that we had this arrival come in around this time here. And so there's a change in the data here. Versus I believe this is where it happened at L1. So we can see there's a good delay between the two. So it impacted Stereohead first. And so when we see all of this, we are putting all of this into the DONKI database. And so this is where you can see the coronal mass ejection data. So when we put it in, we're letting you know what spacecraft saw it first. So this is the start time. You'll see like it'll say which catalog. So this is our catalog, the M2M catalog. The start time of the CME based on the coronagraph. So the first brightness we can see in the coronagraph, that's the start time we're going to use. And then whichever coronagraph was associated with that. So in this case, Stereohead had the first glimpse of the CME. But it was also visible by SOHO, C2 imagery, and C3 imagery. And then each entry is given an activity ID that's automatically created by DONKI. We'll populate in where we believe the source was from, if there's an active region associated with that source, and then we'll start clicking off any keywords that may be useful for the research community. So we saw very front bright. It looks like a halo CME. There was a solar energetic particle event associated with it. The source included a flare. There was post-eruption arcades visible. There was filament material, moving opening field lines, dimming on the solar disk, and then any UV wave, and then any morphology keywords that I think we're going back and reviewing these, but if there was the possibility of seeing a flux rope and shock candidate with it, and then if there was any other notable morphology of the CME itself. And then we'll enter in a note into it. So I detailed out what I saw, where I saw it, what I believed was the source, and then what imagery I saw the source in. And then this little ID here is just a link to the notification we sent out to NASA missions internally. And then if you scroll down the page, you'll actually see this side of it. So this is where I think a lot of people get confused. We have this long list of CME analysis. So when I did it, it was very preliminary. We only had a couple images, and then there was a downlink going on. So I could only do so much to get initial parameters. And so Tony and I were working that day, and we can see that the initial thing was we had this preliminary analysis with SOHO imagery currently downlinking, preventing from further triangulation. That was the best we could do at the time. And so we could see that the parameters that we got based off of what we could look at, we had a longitude of 43 degrees, which is pretty off from where the longitude was of the source location, which was around 68. And then we had a latitude of negative 10 degrees, which isn't too bad, not too far off from the actual latitude of the potential source. And then the half width is just based off of how wide the CME could be. And so 45 is usually what we personally try to cap it at. I think there was some research done about that as to why 45 was like the limit you should go, but sometimes we push it. We go to 50 if we have to. For the really large events. But for the most part, we will try to stay under 45 for a half width. And then the T at 21 and a half radii is calculated by the measuring tool we use. So all of these parameters come out based off of how we're analyzing it. And then there's a classification system in DONKI, which this is, I believe, specific to DONKI. It's not something that is done necessarily outside of DONKI, but the classification system is the scorer classification system. So O-type CMEs are one way. And then we have, which are usually pretty fast CMEs. And then we have C-type CMEs. And we have, trying to think what other C we have. So there's S-type, which is the slowest. C-type are common, O-type are occasional, and then we have R-type, which are rare, and then we have, I think there's ER or there's E, I can't remember, but it's extremely rare, which I don't think I've ever seen one. I know that we've had a rare fast CME, but it was farsighted and headed towards Mars. But so when folks are grabbing our analysis, usually what you want to grab is the ones that have the LE measurement type, which that stands for leading edge. But usually we'll try to explain like bulk. We'll put it in all caps in here just to show like this is the bulk analysis. If you want to grab it, grab this one. And then we try to identify this is the shock analysis. Probably not the one you want to grab for realistic data on arrival and whatnot. And so because this one would be for any of our SEP modeling purposes. So, and we can see the parameters are pretty different. So the shock analysis causes the longitude to be even further away from the source in order to get that halo shape. And then the speed was a lot faster on this one as well. So, and we could see that these are the predicted arrivals here of what the model produced. And then this hyperlink here would bring you to the actual simulation results where you can find that WSA Enlil cone model result. And then additionally, we have, if you scroll down further on the page, you can actually see all of the linked activities that are also in DONKI that may be associated with this event. So when I entered into the CME of itself and scroll down, this is what I see. And then if I scroll down further, I can see this links, which shows the 2 flares that were associated with the event and any of the solar energetic particle events, and then the interplanetary shocks or arrival signatures we saw associated with this event. So that is all in DONKI. It's a wonderful tool to use. It can be overwhelming, and I think there's definitely a way where we could show folks how to use it. But it has all of the data you could possibly ask for. So if you're curious about, okay, what happened with the CME, as long as you know what time the CME started in imagery, you should be able to easily find it in the DONKI database and then see what analysis we had for it. And then, of course, if it is Earth-directed, we will push it to the CME Scoreboard, which I think a lot of folks on Twitter also have seen. And basically, this scoreboard is something that the Community Coordinated Modeling Center hosts, and basically it allows community input of predictions so that this can be used for research purposes later on to better improve models. And so we've got quite a few folks that had entered predictions related to this event. So you can see our prediction at the top here, and then we've got some folks from ASWFC here. We enter in SWPCs on our end. That's an agreement we have with them that we do for them on their behalf. We have some personal folks on here. The Met Office will add their predictions. We also add in SIDCs. That's another agreement we have with them to input it into the CME Scoreboard on their behalf. And then if we have any updated predictions, we'll add those as well. And then there's some other folks like at U of A that add some predictions. So you can see who submits it, what the predicted geomagnetic storm parameters are. And these are based off of different models. So not all of the models are the same. And not everybody has a prediction for the KP ranges. And then you can see how early they added it, and then when it was submitted, how much confidence they may have. So the confidence percentage, I know that on ours, usually when we enter it, it is based off of, it's only associated with our ensemble model outputs, which are even more tricky to explain. But basically, we will measure a CME up to 48 times and then go through, we'll submit that to modeling, and basically it will run each simulation for each of the CME parameters, the different 48 CME parameters. It's 48 unique parameters, and then produce an output. It's kind of like a spaghetti plot, I guess, and then having the cone at the end for like hurricane predictions. But in terms of this, it's space weather related. So you would end up seeing one ensemble simulation result that has just the WSA Enlil results, and that we would sometimes add into here, but sometimes we don't have an opportunity to do an ensemble, so you may not see it on there. But that's usually when our predictions will have a confidence, is that it will produce a confidence percentage based off of how many hits there were in that ensemble. So how many of the 48 members there were that gave a hit, there's this many percent chance of confidence of having an impact. As for other teams, I'm not sure how they produce their confidence percentages. So that would be something that would have to be asked to other teams. And then we can see here the difference in hours would populate based off of what the actual shock time arrival was, which we will enter based off of what we see in the data. But then if there's any chance of any questions on it, we're happy to hear feedback from the community on that. Additionally, we work closely with a group at Goddard called LASSOS, which I'm forgetting the full name of the acronym, but they look specifically at arrival signatures. And a lot of the times we will send our arrivals to them and ask them if they can confirm a start time, what they're seeing, if they can break it apart or anything, if they see anything else, if they don't think it's a CME, if they think it's something else going on. And so we'll get all of that data as well. And have that, which is a lot of what goes on behind the scenes before closing out something on the CME scoreboard. But once it is closed out, you get the difference of prediction time from the actual arrival time. And so you can see here, there's quite a range of predicted shock arrival times and when it actually arrived. So it can be very difficult to do these predictions. It can be very difficult. There's so many pieces that go into play that can change that prediction time by enough. Like if you're using a different WSA Enlil background, that can give you a different output. And so we have all of these things that just come into play where any little thing could cause a different output. So as I mentioned, we have lots of collaborations. So the Community Coordinated Modeling Center is basically our sister group. We have the Space Radiation Analysis group that we work very closely with, and we support with any any of the Artemis missions, or if they have any EVAs going on, we'll provide them any additional forecasts. But we basically talk to them 5 days a week and tag up with them just to let them know what the SEP models are looking like, just for their awareness. So there's always a touching base with them. And then we use Solar Orbiter data and have a nice collaboration with them. Parker Solar Probe, we have a nice collaboration with them as well. And we notify both of those missions if anything is headed their way. We use the stereo data all the time. We use the Solar Dynamics Observatory all the time. And basically, if either of those have any issues, we can notify them while we're monitoring, just to say, hey, it looks like the site might be down. And we'll ask them if anything's going on. So we do have that nice collaboration as well. The James Webb Space Telescope, of course, we supported them with their launch, but we continue to support them with anomaly support. If they have any questions that they think that may be space weather related, we just provide them with an overview once a week of what happened in space weather, so that if they have any questions, they can ask us. Space Weather Prediction Center, we talk to them all the time. It's been wonderful being able to work with them. We basically get to help them sometimes with if there's anything going on with the imagery, since a lot of the imagery ends up being NASA mission related, or if we need help, if we notice like that GOES imagery doesn't seem to be loading on our side, we can talk to them. So it's been a really nice collaboration with them. Maven, we've got actually there's like a whole Mars space weather collaboration going on that includes Maven, some of the other Mars missions, and then it includes the Space Radiation Analysis Group and the Community Coordinated Modeling Center. And so we all work together and are trying to work on improving forecasts towards Mars so that when we are ready to send humans to Mars, we are prepared for that. And then, of course, we supported Artemis, and then OSIRIS-REx we supported, and now it's OSIRIS-APEX, so continuing to support them. And then the Mars Perseverance and Ingenuity mission. So we supported Ingenuity's flight, making sure that there was actually a CME headed towards Mars at the time when Ingenuity was supposed to have its flight. And so we were able to support them with that and just make sure that there wasn't any expected impacts. And that was pretty cool. But so this is the recap of basically our team. So we are a 12-person team, and we're kind of always growing, it seems. But our director is Teresa Nieves Chinchille. She is a new director with our team, but she's been fabulous. She was just with our analyst, Anthony, aka Tony Iampietro, in the UK at one of the conferences that just happened over there. Our deputy director, Michelangelo Romano, and then the handful of analysts, Anna Chulaki, myself, Mary Spencer, Chris Steubenrau, Maddie Anastopoulos, Hannah Herman, Anthony Iampietro, Melissa Kane, and then our newest, Elizabeth. I don't know how to pronounce her last name, but she is our newest member. And then Mary Keenan, which I needed to change that to Pasadena. She recently got married. Is our scientific software developer, for who we would not be able to do half of the things we do without her. So there's a crazy, I mean, our team is growing. It's been great. I know when I joined the team, there was only 4 or 5 of us. So it's been really nice watching the team grow and then seeing what we can do. So you can see that even though we have analysts, they have multiple roles. So there's folks doing anomaly support, validation support. I'm an outreach coordinator, and then we've got training coordinator with Mary Spencer, and then Anna Chulaki as the project manager. So we are ever growing and doing so much. But with that, I just wanted to highlight one of the things that I will be helping out with tomorrow, which is the Aurora Source Reportathon, which I think a lot of folks here would probably appreciate, because most of you are Aurora chasers. And so I personally only saw Aurora for the first time within the last few weeks. So I guess it's been a month now. But there's going to be lots of fabulous prizes, as you can see. I actually feel very special. I have some of the swag myself. And I'm wearing the earrings. So shout out to Laura for sending some my way so I could show it off. But this is happening tomorrow from 1 to 4 p.m. Eastern, or 5 to 8 UTC time. So very excited about that. We'll see folks there tomorrow. And with that, I'm happy to take any questions.
Well, thank you for that. That's super fascinating, actually. I always learn a little bit more when somebody goes through and like the whole scoreboard. I'm like, oh, that's what that means.
Yeah. So the scoreboard stuff, I will say, I did pull it up. So CME Scoreboard is very interesting, and I'm happy to, like, if people have questions, I'm happy to kind of walk through this a little more in depth. But we personally, like, I have a login and everything, and we go in and we'll add the CMEs to the scoreboard. Sometimes other groups have the ability to add the CMEs themselves if they have their permissions to. But then they're hyperlinked to the DONKI entry. So you can actually go and look at the link and see the associated DONKI entry. and get the details about it in DONKI and see all of the analysis done, if there's any notes, if it was modeled, and then you can see all of our notifications we sent to NASA missions related to it, and then if there's any linked events. So this was the X4.5 flare related CME, and we can see that it had an impact at Earth. There was a geomagnetic storm. We had an impact recorded at Stereo Head, and then there was some modeled SEP stuff going on, and then SEP events as well. So kind of was just a full event there. I know it was very close to a magnetopause crossing, but it didn't end up happening. So
yeah, it was an interesting one because it was
yes,
it was quite wide for being so far in the east.
Yes, yeah, it was a very impressive event, honestly. I'm really impressed with it. So
that's awesome.
Well, we do have a couple questions. First one was regarding the INLO model. Why do all the INLO models look swirled? And I guess to expand on that, can you describe a little more about the structure of maybe the lines that are connected to the planets and the satellites?
Sure. So I'm just going to pull up this most recent one. So this is the one from the X4.5 flare. So Earth is this yellow dot here. You're looking, this section, you're looking top down. So if you were hovering over the sun and looking straight down, you're looking at the ecliptic plane. And basically what you're seeing is what's called the Parker spiral. So the sun constantly emits a stream of solar wind. And in this one specifically, we're looking at the density version of this. So there's, if I go back, there's a link that shows you the velocity version of the background. So it looks a little bit different. But for this, I'm just going to go to the density one. And so basically we can see the different layers of density. So the this bar down here shows you the strength of it. So blue is less dense, and then the greens are more dense, and the closer you get to the reds is even more dense than that. So the CME we can see is pretty thick when it pushes through. And so usually this, looking at the spiral here, we can see if there's a possibility of a high-speed stream coming along. So usually the high-speed streams, in fact, I'm going to make this a little easier. So if I do this real quick. So we can see sometimes the high-speed streams here, which are in the yellows here, because that's where the faster speeds are. So we can see on this same color bar, blues would be lower speeds and then higher up speeds here. So I can see that there's a high-speed stream possibly modeled here based on the background of the sun. So there's usually they ingest images of the sun to try and get a map of what the solar wind may look like and try to model that. And then that model goes into this. And then you get basically the streams. And since the sun is rotating, you get everything is moving out radially, but as it moves, as the sun is moving, it ends up creating that swirl. So if you think of it, if you were to take a tennis ball and you put a string on it and you dunked it in water and you held it and you spun it in one place, even though all the water is escaping out straight, it ends up looking like a swirl as it escapes the tennis ball. So that's kind of what's happening with the sun. The sun is a tennis ball, and the swirl coming off of it, the solar wind, is like the water coming off of it. And then the other lines that are here, so there's the magnetic connectivity lines are these black and white lines, basically just showing what possible magnetic connectivity back to the sun may be from each mission. And then the white line is a current sheath, which I am terrible at explaining, honestly. So I'm not even going to try because I don't want to give you the wrong information. But basically, there's a lot of differences here, and I think the current sheath is usually the difference between your positive and negative polarity with the magnetic field. So you can actually see in this cut. So this cut, basically what we're looking at is we've rotated from looking above to looking from the side of Earth. And so I can see the ecliptic plane here, but I'm looking at Earth from the side as if like maybe I was at Lucy and I just stood there and looked over at Earth. So you can see Earth from that one here. And then you're just seeing the movement of basically the solar wind within this, and then that interplanetary magnetic field polarity from positive and negative just kind of getting streamed along with that current sheath. And you can see the CME going through this one as well. So this one we use to see if the CME is well out of the ecliptic. We can usually see, okay, is there actually any impact to the mission, like to Earth here, or is it going to miss to the north or to the south of it? And then this one on the right is probably the most difficult to explain. In fact, I'm just going to do this so that it's not so overwhelming with seeing multiple things happening. So if you imagine having like a paper towel roll, and shout out to Tamithosco for giving me this explanation, because I personally had a hard time trying to describe it and explain it. So you've got north and south here. So up and down is north and south, but then you've got east and west here in the 180 degrees. So basically, if you took a paper towel and you rolled up along this line here where Earth is, and you unraveled it, you would get this. So it goes from a rolled up version of what you're seeing here, and I'm doing a terrible job at explaining this, so I apologize already. But if you basically unrolled it, you would get a rolled out version of what you're seeing along here. Kind of like how we have the Earth map, and then like if you went from globe to flat, but just specifically along this line is what you're seeing here. So I hope that explained it a little bit. There are lots of missions here, and there's a key at the top to kind of point out which each one is. So we can see this is Lucy, this is Parker Solar Probe, which is starting to approach its next perihelion pass. Mercury and I think it's Bepi Colombo are chilling together right now, and then Solar Orbiter is coming by, and Osiris Apex is here, and then this is Venus. Mars is over here, and then there's another version that's even further zoomed out that goes a lot faster spinning wise, which is the 5.5 AU, where you can see even further out and see Juno and Psyche. Hopefully that answered the question.
Yeah, that was a great explanation, honestly.
Thank you.
I always use the solar minimum, at least, the current sheath to detect then boundaries.
Yeah, the solar sector boundary crossings. Yeah.
That's really the only use I've found myself for it.
Yeah.
Another question we've got on this then would be, for the CME scoreboards, at least the average estimated KP values, what inputs go into calculating those, and how often are they verified?
For the average?
Yeah, we'll just say like an average amount, and then I guess just a guesstimation on a percentage as to how accurate those ranges are generally met for events.
I would not be able to give you a value on how accurate they are. The average of all methods that's seen on here, this is literally just averaging what's on here. But the KP ranges, I can speak for what M2M's do, but I can't speak for what other missions do or other groups do with their methods. So the Moon to Mars results, when we get them back, it's automatically calculated by the model output. So we can look at the results. So if I were to look at I got to find it again. Sorry. If I was to look at this CME specifically, so there's actually timeline data here. So I can look at the timeline data. So this is what the model outputs, and it's showing me, okay, it sees an impact. There's this change in density, in velocity, in magnetic field strength, and in temperature. And so I can see this jump here. And then simultaneously, I can look at this data and see this is what it's producing with the KP output based off of what this increase is. And so I can see that the KP ranges is somewhere between 5 and 8 based off of this. And so you can see the clock angle there. So ours is automatically outputting them based off of what is ingested into the model. So it's looking at the data, and then it's producing outputs, and then we push it into the CME scoreboard. Sometimes we'll look at this and we'll go, whoa, there's no way that's correct. And we may adjust it just based off of what we can tell. So like visually, if we're looking at a CME and it looks very, very faint and it's giving us a KP8 because when it put it into the model, it ran it and it gave it this kind of density, we may adjust it. So that's some of the cases, but otherwise, for the most part, we try not to play with it because it is based on the model. And in order for models to get better, you have to sometimes accept the fact that it's going to have bad outputs.
That's fair. That was the last question for at least chat-wise. Mary Beth or Tanya, do you guys have anything you want to ask in the meantime?
I'm sure Tanya has some things to say. She always does.
But she'll have to come out of being hiding.
No, I find this all fascinating. Like I like listening to everybody, like people like you explain it, and because I get something new out of it every time, because it is a lot. Like,
yeah.
When I first looked at the DONKI scoreboard and I was like, I don't even know what I'm doing.
Yeah. And the DONKI database is overwhelming. I will say that as someone who uses it actively every day. So like we have a search space weather activity. So if you're someone who's never used the DONKI database, you go to DONKI. So you've got this lovely link here that's like hawaii.ccmc.gsfc.nasa.gov/DONKI. And you can go to the search option here. So it's search space weather activity. And then this is where you can see there's different catalogs. It automatically goes to the M2M catalog. And basically with this, you can say, okay, I only care about the most recent flares. And so you could choose to look at flares. You could choose to look at solar energetic particle events. If you want to look for coronal mass ejections, if you want to look at any interplanetary shocks that may have been entered, magnetopause crossings, geomagnetic storms, radiation belt enhancements, high-speed streams, or you just want to look at cone results, you want to look at the model results. You can click on all of these, any of them, and it will, if you click search, it will pop up. If you leave it at all and you click search, so this is from September 13th through the 20th, you can see all of the data that was entered. This is, and it'll go in order as if it was in the drop-down menu as well. So it's looking at all the solar flares first, and these are all the ones that have been entered by the team. And so you can see the class here. In DONKI, we will only add M class and above into DONKI. There are some C class or lower flares in DONKI, and those are usually only because they're associated with an event. But if there is no associated event with any of the C class or below, it will only be M class and above. So that's typically what you see in DONKI. And then all of the directly linked events here, if there's anything associated with it, you can see hyperlinks everywhere. DONKI is full of them. Any of the solar energetic particle events that may have recently happened, you can see that there. And then this is the chaos of all the CME data, which you can see very quickly. You could go through and look for start times here. And then if it was detected by which spacecraft, if there was a suspected source location, and then this is the analysis information. And so, like I mentioned before, there's a type classification system that's specific in DONKI, but I don't know that it's well known everywhere else. And then you can just get the data and then see the results and where the impacts are expected on the right here. And then you can actually click on the hyperlink that would bring you to that simulation page. And then you can click on all of those hyperlinks and get your different simulation results. So it's kind of like a nonstop shop where you can just grab any information you need. And then there's some where the measurement technique may change. So a lot of the times we're using a tool called SwipsyCat, which was that one where basically it looks like this. And so basically we would use this. I'm just loading the recent data, pulling this up real quick. And so this allows us to go through, we can look at difference imagery, and we would analyze a CME that came through. So I can click specifically and see this is C2 imagery and this is stereo ahead imagery, and just click through and kind of look at the data of what's happening recently. So I can see there's some data that is campaign data because Parker Solar Probe is starting to make its approach to the sun. So a lot of the missions go into campaign mode, which then changes how we get the images. But that's kind of a whole nother thing. But if we're not using SwipsyCat, sometimes it'll mention plane of sky, and usually plane of sky may be using SwipsyCat or StereoCat, which is another measuring tool. But usually it just means we're not going to have a longitude because we can't find the source and we can't triangulate easily. So those are the cases where you may only get like one spacecraft, single spacecraft mode, and you can't see a visible source. But yeah, so there's all of that data and lots of it. And then there's the interplanetary shocks listed down here, which you can see which location they happened at. So we do Earth and stereo head currently. I think there's talk about possibly adding in Mars related stuff when we're ready, and once we have that data, but I don't know for sure if that's going to happen and when. And then again, any linked events to that, geomagnetic storming, so you can see, and specifically in DONKI, and this actually plays into the NASA Sun posts because they use DONKI to produce their list for the NASA Sun social media pages. We do not add in, it's something to do with a NASA related threshold. We do not put in KP5 and above. It's only KP6 and above. So we do G2 storming and above for geomagnetic storms. So G1s get left out in DONKI. I'm not sure entirely why. That was discussed and made prior to M2M's existence, and we just continued as requested. So you won't see anything below G2 in DONKI unless it's part of a specific catalog. And then radiation belt enhancements in here as well. And then high-speed stream, we had one of those. And then all of the modeling we've done, which these are all modeled results. And so you can kind of look and see which CMEs are associated with it. And then which AU version it is. So the 2 AUs are the most common. 5.5 is more rare, but usually just to see if there's an impact to Juno or if there's an impact to Psyche. And I think that's it. And then you can also see the KP ranges based on the model outputs here. So, but yeah.
Very thorough explanation. Actually, that answered the other two I had prepared.
Well, I do want to say thanks for calling out the difference between the bulk modeling,
shock and the bulk,
shock, and why you do it, because that makes sense. If you have to monitor the solar and energetic particle events, which you do because it's important to our satellites, then that makes a lot of sense to have that shock modeling available.
Yeah. So those go into the CME Scoreboard, which is this intense looking thing, which is too complicated to explain right now. But it goes into these lovely CME Scoreboards, which are being used to work on model validation so that we can validate CME models for human exploration.
Yeah, which is, we all know, very important. Those poor astronauts up there don't have the magnetosphere or not magnetosphere, but atmosphere to protect them.
Yeah.
So yeah, especially if they're going to Mars.
Yes. Yep. Definitely.
More power to them. I'm perfectly fine being down here.
I agree. I'll happily protect you from the safety of my home.
Yes. Like, I'm good.
My body couldn't take a launch. That's too rough.
I mean, I want to go into space at some point, but I'm definitely like, Mars, I don't know if I could do that. I don't know if I could personally do that. I think I would be too scared.
Yeah, I don't have that, whatever that gene is that people get, that super crazy exploration thing. No, I'm good.
Nope.
So anyway, if we don't have anything else, I guess I could say thank you very much for coming.
Yeah, thank you. I'll leave this up if anybody wanted to grab contact info.
Yeah, absolutely. It's been great. I know I've chit-chatted with you back and forth here and there in different chats, and so it's nice to actually finally see you.
Yeah.
That's super fun.
I guess last second reminder as well about the reportathon tomorrow for people.
Yes.
We're all going to be here.
Register.
It is a lot of fun. It really is. I did it last year and it was just a ton of fun. So I'm looking forward to it again.
Yeah, me too.
Yeah, especially now that you saw it.
Yeah, I get to add reports. I feel so I'm so excited. The background actually is one of my photos from my phone.
Nice.
But I'll tell you what, it is a totally different vibe, like doing all of the analysis, doing the forecasts and everything, and then being able to actually see the results is just
it is a huge thing.
It's awesome. So And I wasn't even working when I saw it. I just knew my team was busy. I was on vacation.
Yeah. It's like, yay,
sorry guys, but I saw it. Thanks.
I love it. Alrighty. Well, if that is it, I will end the live stream for everybody, and then we can chit chat a little bit afterwards. But
sounds good to me.
Thanks, everybody.
Well, yeah, thanks for coming. Thanks for coming by, Carina.
Thanks for having me.
Yes. Maybe we'll have you back on again if anything exciting happens.
I love that.
All right. Well, for now.